And so we are pleased to have Boyu tell us about detection results for Khovanov homology. And I'll mute and let him take it away.
All right, thank you very much for having me here. It's a great pleasure to give the talk. I actually have given this different versions of this talk a couple of times before, so please excuse me if you have heard some of these in other occasions. So today I'm going to present a result on several detection properties for Khovanov homology on links. And let me start by giving a very brief review of the history of Khovanov homology. So the Khovanov homology is a categorification of a link invariant called the Jones polynomial. In the 1980s, Jones discovered a polynomial invariance for oriented links in S3 by looking at the diagrams of the links. And of course, here we're thinking of knots as a special case of the links. So the Jones polynomial is also an invariant for oriented knots. And here's an example of a possible knot diagram. We see that it's represented by an immersed S1 or immersed disjoint unions of S1 in the plane, where at each self-intersection, we label one of the arc as the arc above and the other arc as the arc going below. So the Jones polynomial is characterized by the following two properties. The first one is the skyline relation, which tells us that if L0, L plus, and L minus are three oriented links with identical diagram, except that near a small neighborhood, L plus, L minus, and L0 are given in these three pictures, then their Jones polynomials should satisfy this equation. And the second condition is a normalization condition, which requires that on naught has Jones polynomial equal to 1. It turns out that these two conditions uniquely specifies the definition of a Jones polynomial for an arbitrary link. And also, because the two conditions are given in purely combinatorial language, so it's also pretty straightforward to compute the Jones polynomial of any given link diagram using the two relations. So as an example, if we want to compute the Jones polynomial of an on-link with two components, then we can take L plus, L minus, and L0 to be given by these three pictures. Then here is the skyline relation. So notice that the first picture and the second picture are both on knots. So that implies by the second equation above that the on-link with two components has Jones polynomial given by this formula. So by the way, although it's called Jones polynomial, we see from this computation that the Jones polynomial is actually a Laurent polynomial in terms of the formal square root of variable t. And similarly, if we want to compute the Jones polynomial for more complicated links, for example, if we look at this hop link that's oriented in a way that the linking number is positive 1, then if we apply the skyline relation on this particular crossing, we get this is L plus, this is L minus, and this is L0. So here's our skyline relation. But now notice that L minus is just is isotopic to an on-link with two components. L0 is just on naught. So in conclusion, we see that the Jones polynomial of the hop link that's with linking number 1 is given by this formula. And in general, by an induction argument, it's pretty easy to see that the Jones polynomial can always be computed in this way by induction on the number of on the crossing numbers and using the skyline relations iteratively. So a long-standing question about the study of Jones polynomial is whether the Jones polynomial distinguishes the on-knot. In other words, if we assume that there's a knot such that its Jones polynomial equals 1, the question is the knot K always isotopic to the on-knot? Now, although this conjecture is still open until today, now we do know that there are a lot of detection results of a categorification of Jones polynomial, and that is called the Khovanov homology. So now let me move on to discuss some of the background of Khovanov homology. The Khovanov homology is a homology invariant for oriented links that was discovered by Khovanov in the 1990s. And if we are given an oriented link S3, then Khovanov homology assigns this link a bigraded linear space. And here, for simplicity, we're taking the coefficient ring to be 0 over 2, although for the definition of Khovanov homology, the coefficient ring can be an arbitrary commutative ring. So the Khovanov homology can be thought of as a categorification of the Jones polynomial in the sense that if we compute the Jones if we compute the Euler numbers of the Khovanov homology with one of the gradings, which is called the homology grading, then we get a sequence of integers, and those integers recover the coefficients of the Jones polynomial. Well, in fact, it recovers the coefficients of the unreduced version of the Jones polynomial, which is 1 minus t, well, actually square root of t minus plus like 1 over square root of t times the previous version of the Jones polynomial that we just discussed. So in this sense, the Jones polynomial is recovered by the Euler numbers of the Khovanov homology, and therefore it can be thought of as a categorification. The Khovanov homology can be thought of as a categorification of the Jones polynomial. And also, if we have a cobordism between two links, then there's an associated morphism between the corresponding Khovanov homology. So in this sense, Khovanov homology also has a certain kind of functoriality property. It is now known that Khovanov homology is a very useful tool in the study of knots and links. For example, by a work of Jake Rasmussen, we know that the Khovanov homology can be used to give a lower bound for the smooth slice genus of knots, and therefore the Khovanov homology has yielded the first combinatorial proof of the Milner conjecture. And more recently, Peter Lambert-Cole has a paper that reproduced the adjunction inequalities from gauge theory and Floer homology using combinatorics based on an argument that uses Khovanov homology. But still, because Khovanov homology is defined in a purely combinatorial language, its connection with topology is not yet fully understood. And a general question that we can ask about Khovanov homology is, like, what topological properties of the knot or link can be reflected by Khovanov homology? Or more concretely, we can ask what are the knots or links that can be distinguished by Khovanov homology? Well, a breakthrough in this study in this question was obtained by Kronheimer and Morovka in 2010, where they proved that the Khovanov homology indeed distinguishes the on knot from the other knots. You recall that previously we have said it's not known whether the Jones polynomial distinguishes the on knot. But now we know that if we consider the categorification of the Jones polynomial, then we do have a theorem that tells us that the Khovanov homology detects the on knot. And in fact, if we look at the statement of their theorem, it's even stronger than just having an on knot detection property. What they actually proved was that the rank of the Khovanov homology already distinguishes the on knot. So in the statement of theorem, all we need to know is that the rank of the Khovanov homology of the knot is the same as the rank of the Khovanov homology of the on knot, and we don't even need to a priori know the grading of the Khovanov homology to conclude that K has to be the on knot. And later, this result was generalized by Batsansi and Hayden-Ni to the case of on-links, where they proved that the Khovanov homology also distinguishes the on-link from the other links. But here in their statement, we have to assume that the Khovanov homology has, as a bi-graded module, agrees with the Khovanov homology of the on-link. In other words, in the on-link detection theorem, we not only need to know the rank of the Khovanov homology, but also need to know the bi-grading of the Khovanov homology. The detection properties of Khovanov homology has been studied by a lot of people since the works of Kronheimer and Morovka and Batsansi and Hayden-Ni. And now we know that by a theorem of Baldwin and Sivak, we know that the Khovanov homology detects the trefoil, and later we know that it detects the Hopf link. Last year, Lipschitz and Sharka showed that it distinguishes split links from other links. And Gage-Martin showed that the Khovanov homology distinguishes the link T26. And more recently, Baldwin, Dolling, Levin, Littman, and Sastanovich showed that the Khovanov homology distinguishes the figure 8 knot. So the main result that I would like to present today discusses the detection property of Khovanov homology for links discusses a detection property when the link has minimal Khovanov homology. So a general property of Khovanov homology is that if we have a link L that has n components, then the rank of its Khovanov homology is at least 2 to the nth. And also notice that the orientation, although the Khovanov homology depends on orientation of the link L, the rank of the Khovanov homology is actually independent of the orientation. And changing orientations of the link only shifts the overall grading of the Khovanov homology. So when we talk about the rank of the Khovanov homology, it makes sense to refer to this rank even if we have an unoriented link. And the question asked by Barton Seed regarding this lower bound on the rank of Khovanov homology is that, can we classify all the links such that the rank of its Khovanov homology achieves this lower bound? And as we may expect, one of the examples that the link achieves the lower bound on the rank of Khovanov homology is the unlink. In fact, if we compute the rank of the Khovanov homology of unlink with n components, we'll see that it's always 2 to the nth. But it turns out that the unlink is not the only example where the lower bound can be achieved. In fact, if we compute the Khovanov homology of the Hopf link, then it can be shown that it has rank 4, and therefore it also achieves the lower bound. But more generally, there's a Kuhnert formula for the connected sums of 2 links, and also for the disjoint unions of 2 links on the rank of Khovanov homology. So as a consequence, any link that can be obtained by the disjoint unions or the connected sums of the unlink or the Hopf link will all satisfy this, will all achieve the lower bound on the rank of Khovanov homology. So here are 2 of the examples of such links. The first link is a connected sum of 2 Hopf links. And by our previous argument, we know that its Khovanov homology has rank 8. And the second link is a connected sum of 3 Hopf links. And its Khovanov homology has rank 16. And more generally, we can have more complicated links given by further connected sums and also disjoint unions from this kind of links. In the earlier paper of Batz and Seed, they wrote a computer program to compute the Khovanov homology of a big family of links. And from that computational evidence, they conjectured that actually all such links that achieve the lower bound on the rank of Khovanov homology should be given by this construction. And the first result I would like to present today is that we actually have a positive answer to the question asked by Batz and Seed. And we proved that indeed, if a link L achieves the lower bound on Khovanov homology, then it has to be given by connected sums and disjoint unions of Hopf links and unknowns, and therefore, therefore we can easily find a complete classification of all such links using combinatorial language from this characterization. And using similar arguments, we also obtained some other detection results of the Khovanov homology. In fact, we also studied the classification of links whose Khovanov homology has an upper bound. And in this case, we proved that if we have a link, or here a link can be either a link with 1 component, which is just a node, or a link with at least 2 components. And if we assume that this link has Khovanov homology of rank less than or equal to 8, then we obtained a complete classification of all such links based on earlier works of Batz and Seed and Baldwin-Sivak. On the list, we have the unlink with at most 3 components, or the left-handed or right-handed trefoil, and also the Hopf link, connected sums of Hopf links. And then there's one more link, L4A1, where it's mirror image. And here is a picture of the link L4A1. And we also obtained a classification of links with 3 components whose Khovanov homology has rank less than or equal to 12. Here we also got a bunch of examples given by unlinks and connected sums of Hopf links. And then there's one more example, one more possibility that's given by the link L6 and 1, which is this link. And if we also consider the bigrading of Khovanov homology, then in a joint work with Jiankun Li, and also with Yi Xie, we proved that the Khovanov homology as a bigraded linear space detects the following 2 links. And here we have, and both links are given by a combination of a trefoil and an unknot. And in fact, both of them have Khovanov homology with rank 12. Moreover, there's a variation of Khovanov homology called the Khovanov-Sky homology. The Khovanov-Sky homology is defined by Asida, Pshtistik, and Skura on the trivial line bundles over compact surfaces. So this is sometimes called the Khovanov-Sky homology, or in some literature it's called the sutured Khovanov homology. If the surface is just a disk, then the Khovanov-Sky homology is in fact equivalent to the original definition of Khovanov homology. And in the case if the surface is an annulus, then the Khovanov-Sky homology is also called the annular Khovanov homology, and this has been studied extensively by many people. As another application of the argument that I'm going to introduce, we also obtained a series of detection properties for the annular Khovanov homology, where we proved that the annular Khovanov homology detects the unlink, detects the closure of the trivial braid, and that it distinguishes the braid closure from, it distinguishes braid closures from other braids. And here, the third part of the results above is actually a generalization of a previous result of Grigsby and Nee, where they concluded the same detection property under an extra geometric condition here. And in the case where the surface is a torus, we obtained another detection property for the Khovanov-Sky homology and concluded that in this case, this Khovanov-Sky homology distinguishes the unknot and also the trivial, distinguishes the unlink and also the torus links. Okay, so those were the statement of the main results. And now I'm going to move on to discuss some of the ingredients in the proof of the main result. In the discussion, I'll focus on the proof of the classification theorem for links with minimal Khovanov homology, because the other results kind of follow from the same idea, except that they have different technical difficulties. But before I move on to discuss the proof, let me take a pause here and see if we have any questions or comments so far. All right, so now let me start to discuss the ingredients of the proof. So the first ingredient of the proof is the tool engage theory, right? That is the instanton Floer homology. So the instanton Floer homology was based on ideas of Donaldson and Floer, and the version that we're going to use here is mostly developed by Khovanov and Mravka. The setup of the instanton Floer homology is as follows. We take a closed oriented three manifold Y, and for technical reasons, we also need to specify a homology class in the first homology class of Y in Z/2 coefficients. In a lot of cases, it's helpful if we visualize this homology class as represented by the fundamental class of a closed one manifold embedded in Y. And we need to assume that there exists an oriented surface in Y that intersects omega at an odd number of points. And in fact, this is equivalent to saying that omega is a non-zero homology class. The introduction of this non-zero homology class is just to make sure that in the later discussions, we don't have any reducible connections in the moduli space, and therefore everything will work out in gauge theory. So in the early works of Floer and Donaldson and also Khovanov and Mravka, they developed a theory where we can define an instanton Floer homology group, which is a homology invariant for the pair Y and omega. And in fact, roughly speaking, this instanton Floer homology group is an infinite dimensional Floer homology of a perturbed Chern-Simons functional on the space of SU3 connections on Y, where the SU3 bundle is specified by requiring that its second Schlieffmann-Huene class is dual to the fundamental class of omega. And also before the perturbation, the critical point set of the Chern-Simons functional can be described by a character variety of the fundamental group of the complement of omega, if we also require that the holonomy around omega is given by -1. One of the basic properties of instanton Floer homology is that it behaves nicely under a surgery operation for the three manifold, and that is called an excision formula. So to introduce the excision formula, we have to introduce some extra notations. So if we have a surface sigma embedded in Y with genus at least 1, and if we further assume, again for technical reasons, that intersection number of sigma with omega is odd, then first of all we have two operators that can be defined on instanton Floer homology, called mu sigma and mu point. And this is the idea of the mu class or the mu actions can be also found in the original works of Donaldson in the early 1980s. Roughly speaking, those mu maps are defined by chopping down the moduli space using the fundamental class, using the slant product by the fundamental classes of sigma and the fundamental class of the point. So in particular, those operators only depend on the homology class of sigma. It can be proved that the operator mu sigma, so from now on, let's assume that our instanton Floer homology has C coefficients so that we can talk about eigenvalues and eigenspaces more easily. And it turns out that the operator mu sigma has eigenvalues less than or equal to 2g minus 2, and the operator mu point has eigenvalues contained in the set plus minus 2. So we define a subspace of the instanton Floer homology to be the simultaneous generalized eigenspace of those two operators with eigenvalues 2g minus 2 and 2. And if we define this space, then Khovanov and Mumford proved that under a certain surgery operation, this particular subspace of instanton Floer homology always remains the same. More precisely, if we take two different surfaces that are disjoint and intersect omega in the same number of points inside Y, and if we fix a diffeomorphism from one surface to the other, then an operation we can do is to cut this three manifold open along those two manifolds and then glue it back using the diffeomorphism. And this operation may change the instanton Floer homology of the three manifold, but it turns out that if we only look at the particular subgroup associated with the surfaces, then the subgroup are actually isomorphic to each other after this excision operation or surgery operation. And in particular, if G equals 1, this is pretty much equivalent to the original excision formula of Floer. So the first ingredient in the proof of our detection results of Khovanov homology is that we generalized the excision formula to a singular setting. And that is saying that we have a similar excision formula for a singular version of instanton Floer homology. Well, the singular instanton Floer homology was developed by Khovanov and Mumford as a generalization of the previous version of instanton Floer homology, where now, in addition to having a three manifold, we're also allowed to have a possibly empty, a smoothly embedded link that is contained in the three manifold. And similar to the previous discussion, we need to choose auxiliary data. We need to choose an auxiliary data set that's represented by a properly embedded arc or one manifold in the pair YL, so that we can avoid reducible connections in the later discussions. And we need to assume that there exists an oriented surface in Y minus L that intersects omega at an odd number of points, or there exists an oriented closed surface Y that intersects L at an odd number of points. So this is, again, just a technical condition to make sure that when we talk about the moduli spaces of critical points, there's no reducible solutions. So Khovanov and Mumford developed the instanton Floer theory in this setting, where they defined instanton homology for the triple Y L omega. Roughly speaking, the singular instanton Floer homology can be thought of as a variation or a generalization of the original version of instanton Floer homology by thinking of the manifold Y as an orbifold, where the link L is the singularity of the orbifold, and we also assume that all the all the points on the link L has a stabilizer group Z/2. And this class omega is specifying an orbifold isosceles bundle over the orbifold YL by requiring that the second Schlieffel-Koenig class of the orbifold isosceles bundle is dual to the fundamental class of omega. So morally speaking, that's kind of the idea of singular instanton Floer homology. So similar to the setup of the previous excision formula, if we have a surface sigma in Y that may or may not intersect the link, we can define the two operators mu sigma and mu point, and we can define the simultaneous eigenspace of these two operators with eigenvalues 2g plus n minus 2 and 2 as a particular subspace of the singular instanton Floer homology group associated with the surface sigma. So the first ingredient in the proof of our main theorems is that we obtained a singular version of the excision formula for instanton Floer homology, where we concluded that if we have two surfaces, but in this case, the two surfaces are allowed to intersect the link. And in this case, if we cut open the three manifold along the two surfaces and then glue them back, and we still have an isomorphism that tells us that the instanton Floer homology associated with sigma before the surgery is isomorphic to the corresponding group after the surgery. And by the way, if sigma has genus 0, then this is actually a thesis project of an earlier student of Kraheimer, and it was proved by Ethan Street in 2012. Although I would say in Ethan's proof, the computation relies essentially on the genus 0 assumption, and his argument doesn't really work for the high genus case. So that was the first ingredient of the proof of those detection properties. And then the second ingredient is a package of Gabay on sutured manifolds, which was later adapted to the setting of Floer theory by Juhas. We recall that a balanced sutured manifold, by definition, is a compact-oriented three manifold together with some extra structures on the boundary. Where on the boundary, we have a collection of disjoint-oriented circles, such that if we remove the tubular neighborhoods of the circles and call them A gamma, then the complement of the boundary is decomposed into two parts. One part is called R plus, the other part is called R minus. So a typical example that we usually keep in mind on a sutured manifold is that we can take a compact surface with boundary and consider interval times this surface. So the product space of the interval and the compact surface with boundary is actually a three manifold with corner. But of course, we can easily smooth the corners so that we can think of this as a three manifold with boundary. And in this case, if we define A gamma to be the interval times the boundary of the surface, and we define R plus to be the positive end of the interval times the surface, and R minus to be the negative end of the interval times the surface, then this would make the product space a sutured three manifold. But for our purpose, we also need to discuss tangles in sutured manifolds. So we define a tangle to be a tangle in a sutured manifold to be a properly embedded one manifold, such that its boundary has to be included in either R plus or R minus. And similar to the previous balanced condition on sutured manifolds, we say that the tangle is balanced if its intersection number with R plus is the same as its intersection number with R minus. And of course, here all the intersection numbers are geometric intersection numbers. So we're actually just saying that the number of boundary points on R plus should be equal to the number of boundary points on R minus. In the 1980s, Charlemagne studied the properties of sutured manifolds with tangles, and in particular, he defined a version of a generalized Thurston norm for surfaces that is embedded in a sutured manifold with tangles. The definition of the generalized Thurston norm is basically identical to the definition of the standard Thurston norm, except that when we take the order numbers, instead of taking the order number to be 2g minus 2, we have to take the order number to be 2g plus n minus 2. And notice that actually this 2g plus n is 2g plus n minus 2 is exactly the same is exactly the same number as the eigenvalue of mu sigma that we were taking previously on the excision theorem. So in fact, most of the proof of the results are based on this coincidence where we have this 2g plus n minus 2 can be exactly extracted from the eigenvalue of the mu map in instanton Floer homology group. So Scharman defined, actually generalized the concept of Taut sutured manifolds of Gabay and defined a sutured manifold with tangle to be Taut if the complement of the tangle is irreducible and R plus minus are incompressible in the complement of tangle. And also there's no closed component on R plus and R minus, but more importantly, if R plus and R minus both minimize the generalized Thurston norms with respect to the tangle T. And the reason that the setup of sutured manifolds with tangles can be used in our discussion of Floer homology and Khovanov homology is that we can adapt an argument of Kroheimer-Mrówka and using our previous singular excision theorem to define an instanton Floer invariant for sutured manifold with tangles. So the construction is as follows. If we take a sutured manifold, then there's a way to glue up R plus and R minus and then fill in some auxiliary part in the manifold to obtain a closed Floer manifold. This was actually a construction due to Kroheimer-Mrówka. And in particular, if we have a product sutured manifold, say I cross F, then their construction first fills in the surface F with boundary to a closed surface, and then just glue R plus and R minus together to obtain a closed Floer manifold given by S1 times that closed surface. Now, if we have a tangle in this Floer manifold, then if we assume the tangle is balanced, we can also make sure that by choosing the gluing map carefully, we can make sure that the image of the tangle in the closed manifold is a link, so that all the positive side of the boundaries are glued together with the negative side of the boundaries. And this gluing is actually not unique. So for a sutured Floer manifold, there are infinite many different ways of gluing the boundaries and obtaining a closed Floer manifold. But because of the singular excision formula, we can use that to prove that all the triples that we can obtain from this gluing procedure will all yield isomorphic instanton Floer homology groups. And therefore, we can use that instanton Floer homology group as the invariant of our triple. So here, by definition, we're defining the sutured instanton Floer homology group as of the sutured manifold with tangle to be the subgroup of the instanton Floer homology group of the triple associated to a surface sigma, where Y here is the closed manifold obtained from the sutured manifold using Kroheimer-Mrówka's construction. L is the image of the tangle. Omega is some auxiliary data that has to be defined technically, and sigma is like one of the gluing surfaces when we take in the gluing construction of Y. And we also follow the notation of Kroheimer-Mrówka and denote the Floer homology invariant of this triple to be SHI and gamma T. So similar to the other versions of Floer homology and also sutured Floer homology, the sutured Floer invariant of tangles that we defined satisfies the following two conditions. First of all, if the triple is taut, then its sutured instanton Floer homology must be non-vanishing. And second, if the sutured instanton Floer homology has rank 1, then this triple has to be given by the product of interval with a punctured surface. So in some sense, these two statements are analogous to the tautness detection results and also the fibration detection results of the other versions of Floer homology theories. Okay, so now with all the preparations above, we can now discuss the proofs of the main results. Again, I'll only focus on proving the classification theorem of links with minimal Khovanov homology, because the other detection results kind of follows from from a combination of similar ideas and some other technicalities. So to prove the classification theorem for all the links whose Khovanov homology have minimal rank, we have to start with the case where n equals 2. When n equals 2, the statement becomes the following. If we have a link with 2 components, and if we assume that its Khovanov homology has rank 4, then we have to show that the link is either the on-link or the hop link. And how can we prove this result? Well, let's first introduce some notations, and let's take K1 and K2 to be the 2 components of L. Then by a spectral sequence of boson seed, we know that there's a spectral sequence whose second page is the Khovanov homology of L, where the limit of the spectral sequence is the tensor product of the Khovanov homology of K1 and Khovanov homology of K2 up to some shifting. So there's a rank inequality. In fact, we know that the rank of the Khovanov homology of L is bounded from below by the product of the rank of the Khovanov homology of K1 and the rank of the Khovanov homology of K2. And now, if L achieves the lower bound on the rank of Khovanov homology, then that implies that every one of its components must also achieve the lower bound on the rank of Khovanov homology. So by the unknown detection theorem of Khovanov-Murhovka, we conclude that both K1 and K2 must be unknowns. And now we take a ciphered surface of K1. We'll recall that K1 is already known to be an unknown, so its minimal genus ciphered surface is just a trivial disk. But instead of taking a ciphered surface whose genus is minimized, we're going to take a ciphered surface such that it minimizes the value of 2g plus n, where g is the genus and n is the intersection number, is the geometric intersection number of the ciphered surface with the other component K2. And here, of course, without saying, we're requiring all the intersections to be transverse. So geometric intersection number is just counting the number of intersection points. And now we consider the following manifold. We first, K1, well, we know that K1 is a trivial knot in S3. So we consider the complement of a tubular neighborhood of K1 in S3. And so we know that is a solid torus. And then sigma, since sigma is a ciphered surface of K1, so the intersection of sigma in the complement of the tubular neighborhood of K1 is a properly embedded surface whose boundary circle is the meridian of the solid torus. And now if we cut open this solid torus along sigma, we're going to obtain a 3-manifold with boundary. And this boundary has a natural sutured structure because we can take A gamma to be a tubular neighborhood of the meridian of the solid torus. And then we can take R plus and R minus to be the 2 sides of the surface sigma. And we can also take T to be the tangle given by the intersection, just the intersection of K2 with the 3-manifold. Or in other words, K is just whatever we obtained after cutting the 3-manifold open along sigma. Now, because previously we have taken sigma such that it minimizes 2g plus n, so the R plus and R minus of the boundary of M are both generalized Thurston norm minimizing. And because the background manifold is obtained from S1 cross T2, it can also be proved that the resulting manifold has to be irreducible. So as a consequence, we know that the resulting triple MT gamma is taut. And therefore, we know that its sutured instanton for homology must be non-vanishing. So now we discuss 2 cases. In the first case, if 2g plus n equals 0, then that means g equals 0 and n equals 0. So sigma is a disk and it's disjoint from K2. And therefore, the link L is just obtained by a disjoint union of K1, K2. And because we know that K1, K2 are both unknowns, so that implies that L is the on-link. And now if we assume that 2g plus n is positive, then by the spectral sequence of Khovanov-Murhovka, we have a rank inequality between Khovanov homology and instanton Floer homology. And in this case, we know that since the Khovanov homology has rank 4, well, if we look at the statement of Khovanov-Murhovka, it's actually it's actually a rank inequality from the reduced Khovanov homology to instanton Floer homology. So the Khovanov homology has rank 4 implies that the reduced Khovanov homology has rank 2. So a corresponding version of instanton Floer homology has rank less than or equal to 2. But now recall that our sutured instanton Floer homology group for the triple is defined by a subspace of an instanton Floer homology by taking eigenvalues and eigenspaces. And the eigenvalue in this case, well, actually previously in the definition, the eigenvalue is 2g plus n, is 2g plus n minus 2. But in this, like, if we spell out all the details, actually in the definition of sutured instanton Floer homology, the eigenvalue is taken to be 2g plus n because we took some auxiliary punctures on the surface. So this sutured instanton Floer homology of the triple is given by the eigenspace of eigenvalue 2g plus n. But there's also a symmetry. There's also a symmetric property of the mu map, which tells us that eigenspace of eigenvalue lambda is always has the same dimension as the eigenspace with eigenvalue negative lambda. So there's a conjugation action on the instanton Floer homology group that flips the signs of eigenvalues. So if 2g plus n is positive, that means like if the dimension of the eigenspace of eigenvalue 2g plus n is the same as the dimension of the eigenspace of negative 2g minus n. Now, if the total space has rank at most 2, then that means this one particular eigenspace has rank at most 1. But on the other hand, we also said this manifold is taut, so its instanton Floer homology must be non-vanishing. And therefore, in conclusion, we know that this instanton Floer homology must have rank exactly 1, and therefore the triple is a trivial product. And if we translate this conclusion back to the topology of knots, then that is just saying that our knot K2 is given by a braid closure in the complement of K1. So now we can flip the rules of K1, K2 and conclude that we also have K1 is a braid closure in the complement of K2. And in this case, the link L is actually called a mutually braided link. And this is a kind of link that has been studied extensively by Morton in the 1950s. And in particular, Morton studied the properties of their Alexander polynomials, of such links. So by another spectral sequence of Darling, we know that the rank of Khovanov homology bonds the rank of link Floer homology, which will bond the number of terms of 1 minus x times 1 minus y times the multivariable Alexander polynomial of the link. So since the Khovanov homology has rank at most 4, we conclude that this polynomial has at most 4 terms. But by the previous works of Morton, we know that the multivariable Alexander polynomial can be computed by the Bureau representation of braids. So we will obtain some restrictions on the topology of this braid. And in fact, if we look carefully at this construction, at these restrictions, then using an elementary argument, we can conclude that the braid represented by K1 and K2 on the complement of the other component must be trivial with 1 strand. So in other words, that means the link L must be the Hobbes link. So that was the proof of the main result in the case when n equals 2. And now let's move on to discuss the proof of the general case. Well, in this case, we used an induction argument on the value of n. So suppose there's a hypothetical counterexample with the minimum value of n, and we will try to deduce a contradiction. So by the previous arguments, we know that n is at least 3 because we already proved the result for n equals 2, and n equals 1 follows from Korheimer-Moravka's detection property. And also, by the same argument using Batson-Seed spectral sequence, we know that every component of L is an unknot. But actually, the Batson-Seed spectral sequence tells us something even stronger. We not only know that every component of L is an unknot, we also know that every subset of L, or so every sublink of L, also achieves this lower bound on the rank of Khovanov homology. So by the induction hypothesis, since we're assuming that L is a counterexample with minimum n, we know that every sublink of L is already given by connect sums of Hobbes links and unknots. Now, if we take one component K of L, and as before, study the property of its cipher surfaces and try to minimize the value of 2g plus n. Then we can see that using a similar argument, we can show that it's 2g, the value of 2g plus n has to be less than or equal to 2. And therefore, if we also look at the linking numbers, we can show that n has to be non-zero. So therefore, the only possibility is that g equals 0 and n equals 2. So that means that every component of L must bound a separate surface with genus 0 that intersects the other components as 2 points. And now we look at the complement of the component K. Then, well, again, by some spectral sequence, we know that L prime achieves the minimal. So let's call L prime to be the complement of K. Then we know that L prime achieves the lower bound on the rank of Khovanov homology. So by the induction hypothesis, L prime must be given by connected sums and disjoint unions of half links. But a further combinatorial argument can show that L prime has to be the connected sum of n-1 half links. Because if L prime is anything else, we can always throw away some components from L prime to obtain a smaller counterexample using the QNAS formula. So in other words, L prime is the link that looks like this. And we also know that the link K must have linking number 1 with the first component and linking number ±1 with the last component, and also has linking number 0 with all the other components. And so the previous discussion on the ciphered surface of K implies that the knot K bonds a disk that intersects the first component at one point and the last component at one point, and is disjoint from all the other components. Now we can choose an orientation of L prime such that the algebraic link number of L prime with K is 0, because the first component contributes ±1 and the last component contributes ±1. And if you just choose the signs correctly, we can make those two ±1s cancel. And now if we use a similar instanton Floer homology argument, but on the ciphered surface of K, so now if we choose a ciphered surface of L prime and try to minimize the value of 2g plus n, then by a similar argument as we did before, we can show that in this case, we must have 2g plus n equals 0. So that implies that this link L prime must bound a ciphered surface after we oriented it correctly. It must have a ciphered surface with genus 0 and is disjoint from K. But notice that L prime is actually a fibered link. So the minimum genus ciphered surface is unique up to isotopy. Therefore, there are only two possibilities for the topology of the ciphered surface, depending on the two different choices of orientations of the orientations on the first component and the last component. Either the ciphered surface looks like this, or the ciphered surface looks like that. And we know that the last component, the nth component K, is a knot that is disjoint from the ciphered surface and also bonds a disk that intersects the first circle at one point and the last circle at one point. Well, it turns out that although this is a non-trivial topological argument, but we can show that there are only two links that can possibly satisfy all the conditions above at the isotopy. And then a direct calculation can show that the Khovanov homology of both of the links have rank strictly greater than 2 to the nth, and therefore we obtain a contradiction, so the main theorem is proved. So, all right, so that was the proof of the main result. And for the rest of the talk, I'd like to also discuss a sketch of the proof of the excision formula, because I think that's a main ingredient of the proof. But before discussing that, let me take another pause here and see if we have any questions or comments so far.
Are the links that those two links easy to describe? Or are they well something?
Yeah. So the link look like this. So if we have our link K has linking number 1 with this component, linking number 1 with that component. So it's like so we have the K the K winds around this component and then goes down and then starts to twist and then twists as multiple times and then it links with that component. And the twisting number has to be either something like n over 2 or n over 2 plus 1. Like, I think those are the two possibilities.
That to make the Alexander polynomial come out, right?
That's from the topology. So because, well, in other words, so another way of describing the link is that if we take an arc on the Seifert surface that starts from here and goes across the crossings alternatively. So it goes the top crossing first, and then this crossing, and then that crossing, and this crossing, and then it goes all the way to the other side of the link. Then that's an arc on the Seifert surface. And then if we take a disk in R3 that intersects the Seifert surface exactly on this arc, then the boundary of that disk is the knot K. And so that's from the topological argument, and actually that disk is the Seifert surface of the link K that's described here. But then we can compute. We actually didn't really compute the Jones the Khovanov homology. We just computed this Jones polynomial, and prove that if we plug in some particular values of Jones polynomial, we can obtain lower bounds of Khovanov homology. And when n is sufficiently large, this is already sufficient to show that the rank is greater than 2 to the n. When n is small, we just look at the knot atlas and check the rank of Khovanov homology directly.
Okay, thanks.
Yeah, thanks. Okay, so now let me move on to give a brief discussion of the proof of the excision theorem. So recall that the excision theorem describes the behavior of the instanton for homology when we cut open the three manifold along surface sigma and then glue back together. So now if we take sigma g to be a Riemann surface with genus G, and if we choose n points on sigma g, then we can consider the following triple. The three manifold Y is given by S1 times this surface, and the link L is given by S1 times this n points, so it's a link with n components, and we just take omega to be the empty set. And in this case, well, by the formal TQFT properties, it turns out that to show the excision formula for the instanton for homology, we only need to prove that the dimension of this particular space is 1. Actually, this follows from the same argument as the original proof of Floer's excision theorem, and also for the excision theorem of Khovanov and Mumford. The excision property can always be deduced to a computation of a particular instanton for homology group and show that it has rank 1. And now there are a couple of ingredients in computing this. It turns out that in all the proofs of the previous excision properties, the strategy was like, we have to compute the instanton for homology completely first, and then we have to figure out exactly like what this subgroup is, and to show using algebraic argument that the dimension of this subspace is 1. But in our case, at least so far, we don't know how to compute the complete structure of the instanton for homology group of this triple. But I guess it's just there's some coincidence that happened so that we were able to compute the dimension of the top eigenvalue without knowing what's happening with the other eigenvalues. So there are few ingredients in the proof. The first one is that, in fact, this instanton for homology actually has a ring structure because we can define a product operation using the pair of pants cobordism on S1. So it has a ring structure, and it's known by previous works of Minute and Street that this ring has to be a deformation, a graded deformation of the cohomology ring, that's of the singular cohomology ring of the critical point set of the unperturbed Chern-Simons functional. But now recall that we said the unperturbed Chern-Simons functional, the critical point of the unperturbed Chern-Simons functional can be write down explicitly as a character variety. And in particular, there's a standard correspondence theory in algebraic geometry that tells us that this moduli space is actually equivalent to a moduli space of stable parabolic bundles. And there's an idea of Mumford from decades ago in algebraic geometry that tells us that we can study the cohomology ring of such moduli space using an observation by looking at the Chern classes of the universal bundle. So if we look at it, because this is a moduli space of vector bundles, so we can construct a universal bundle over this universal space. And if we consider some index bundle over this universal bundle, then we will obtain a vector bundle with rank, with a particular rank that can be constructed, can be computed by Riemann-Roch. And as a consequence, of course, all the Chern classes of this vector bundle with higher degree must be 0 because that's higher than the rank of the vector bundle. But on the other hand, we can write down formulas for those Chern classes using the family version of ITS single index theorem, and therefore that will give us some conditions on the structure of the cohomology ring. So that was the first algebraic ingredient in the proof. And then the second ingredient is that we computed a cobordism map that's given by this picture, where it increases genus by 1. And we know that this cobordism map has a left inverse because we can fill in this cobordism into a trivial cobordism. So it's injective. And of course, this map is also equivariant under the action of the mapping class group. And then the third ingredient is that we considered a cobordism that increases the number of punctures. And similarly, we computed this map directly by looking at the representation varieties and solving the Chern-Simons, solving critical points for Chern-Simons functionals, and show that this map actually is given by the multiplication by a combination of 2 of the generators. But also this map has a left inverse, so it's injective. And now just combining all the algebraic ingredients above, it turns out that we can show that the dimension of this particular instanton Floer homology, the subspace of instanton Floer homology is 1 by an algebraic argument using induction on N and G without even computing the ring structure of the instanton Floer homology group. Okay, so I think that's all I have for today, and thank you very much for your attention. I think I'll stop here.
I'm not sure if Dave is still on. I think he had to go. So let me ask if there are questions for Boyu. I guess whenever you have these kind of classification or detection results, I guess, are you sort of at the limit of what such techniques can give, or do you think there are some more that?
Yeah, we think we have pushed this idea pretty much to the limit. Anything we could thought of, we have like basically already wrote them down. Well, there was something that we really wanted to do, and we tried pretty hard, but we couldn't see how to prove it right now. So in that detection results with Zheng-Kun Li and also with Yi Xie, we proved that Khovanov homology detects the following 2 links, and those 2 links are 2-component links with Khovanov homology rank 12. We actually looked up the Not Atlas website and figured that there are actually only 4 links whose Khovanov homology with 2 components whose Khovanov homology of rank 12, and we can now prove that the Khovanov homology together with a bigrading detects all the 4 links, but it would be nice to have a classification theorem for all the 2-component links of rank 12 as well. So in this classification, we only obtain classification for links with 3 components. And it would be
kind of a sort of structural theorem. You could hope for that. I don't know, somehow like finite, or so given Khovanov homology, there should only be finitely many, or is that actually false?
Yeah, I actually don't know. That's something we actually have once asked Khovanov himself on this, and I think he believes it's not true, but he couldn't think of an immediate counterexample. Mm-hmm. But the reason that our method is probably not very useful in this question is because our result, the strategy of our proofs mostly depends on this braid detection property. So we have to first know that whatever the component is a braid, and then we use properties of braid or braid representations to study the number of strands and the structure of the braid. And that's kind of the strategy that we use. So if we have a complicated link that is not given by combinations of braid closures and stuff, then our method wouldn't be very suitable for that. So as an illustration, so here this link L6N1 is actually a mutually braided link. So this component is obviously a braid in the complement of this trivial component. But in fact, we can also show that So this link is actually, it has 3 components and it's pretty much symmetric. So if we can, so if we take every component, the other components are actually a braid closure. And similarly, if we look at this picture, then that's also given by a braid closure. So that's kind of the reason why we think a classification of links with rank 12, 2-component links with Khovanov homology rank 12 is hopeful, because in fact, in all the examples, they all have this this braid structure. So here, actually, this trefoil is also a braid closure in the complement of this. This is the only counterexample, probably, but still, we can think of this unknot as a braid closure of the complement of the trefoil using the fiber knot structure of the trefoil. So that's some hope. But anyway, so I was saying this method is more useful when we can say something about the minimizing the value of 2g plus n, or whether or not something's a braid closure. And if we have complicated links that neither of those is obvious, then probably this method wouldn't be very helpful.
Anybody else got any further questions, or? Well, let's thank Boyu again for a nice talk.
Thank you very much.
Pitch in and say thank you very much.
Oh, there's Dave. Okay,
Yeah,
sorry.
I am here.
I wasn't sure whether you were there or not.
Thanks, Danny. Thanks, Boyu.
Okay, very good. So I guess next week we have Paul Feenan. That'll be the last for the semester, and well, we'll see when we resume sometime, I suppose, in January.